What? Yeah, now it's working. Hi everybody. Now we're going to have a highly specialized talk about some crazy Linux specifics by Mr. Patterson. Please give him a warm welcome. Thank you.
Good afternoon, and thank you very much for attending this presentation on computer forensics and crypto key recovery from Linux memory dumps. I know that this is a highly specialized talk, and I have a lot of like small printed details. So if you want to like move up closer, if you can't see anything, please do that. My name is Torbjörn Pettersson, and I work as a computer security consultant for a Swedish firm called Nexus Security, and I do some computer forensic work as well as part of my job at Nexus. And it is in this line of work that I've been introduced to computer forensics and crypto key recovery. In the last few years, since the US government decided to change their policy on cryptographic export, there's been a boom, or it starts to flourish, a lot of different cryptographic solutions for especially Linux and other platforms as well. And this has provided us with new tools and new ventures for disk encryption and file encryption that simply wasn't possible before as easily to what we perhaps could call the consumer. The ease and popularity of these tools has provided, or rather given, forensic examiners a formidable challenge, as people who actually have legit paranoia, we could say like hackers, pirates, dissidents, and other people have started using these type of tools en masse. In this presentation, I will try to go into details on how to attack these systems and how to recover the cryptographic keys used when encrypting disk storage and when encrypting loopback files. I'm not the only one who has been doing research in this area. A guy named Maurits Burdach has actually written a really good document and research how to recover other types of information or forensically interesting information from memory dumps. And a guy at IBM named Wietse Venema has also done a lot of research on the Windows platform on how to recover not only cryptographic keys and encrypted files, but also other forensically interesting information such as process list, running programs, open network connections, and such. So there's a number of different disk encryption options for Linux. I've been looking at Cryptoloop and DMcrypt, but there's also TrueCrypt, an open source multi-platform encryption solution. We have LoopIS, that is a kind of a relative to Cryptoloop, and I also believe BestCrypt is what is it called? A commercial version as well. All of these solutions have one thing in common. They have to store the encryption key in memory out of necessity, otherwise it won't be possible to use. There are of course hardware implementations as well, but all of these software implementations share this common weakness that in order to be able to do the encryption or run the encryption algorithm, it has to have the key available in memory out of necessity. When disk encryption is done right, it's virtually impossible to break, and as with any type of security solution, it's never stronger than its weakest link. And I will try to show you how to attack one of those weak links that is in common in Cryptoloop and DMcrypt, namely the fact that it has to store the encryption key in memory. So, of course, one of the prerequisites for doing this is that we have a copy of the memory. And at the end of this presentation, I will go into details on how to actually acquire one of those memory dumps. But I will start out with going into details on how to extract cryptographic keys out of an existing memory dump. So how you actually got hold of this memory dump isn't so much interesting for what we're trying to do, but it comes into play when you're actually trying to perform this attack on someone. So we start out by assuming that you have a memory dump. So the crypto loop. I remember using the crypto loop or something similar to it back in the 2.0 Linux kernel 2.0 series. It was available as patches, and I've been doing some Googling on it, and I haven't really been able to find any information who actually wrote that. But I believe that it is somehow related to the version we have today. Since the 2.2 series, it's been available as patches for the 2.2 and 2.4 and, well, probably 2.6 series as well. What happened was that the US government actually released the embargo on encryption technologies, and what happened then was that we saw the introduction of the crypto API into the Linux kernel for the 2.5 series and 2.6 series, and once that was introduced, the cryptographic layer could be used by Cryptoloop as well, and Cryptoloop has been marked as deprecated in the 2.6 series, and for a number of different reasons it's been replaced by dmcrypt that we will look into later. For a number of different reasons, the patches from kernel I wasn't really as good as people wanted them to be. So for this reason, it spawned different versions. For instance, the loop.is. The author of loop.is has a lot of things to say about the security in Cryptoloop, and I believe it's right in many cases. But I won't go into details on the different shortcomings of Cryptoloop. But Cryptoloop is basically a layer that you can put between an existing file or an existing device. And Linux has the feature of loopback mounting different medias and pretending that it is a device. For instance, you can mount an ISO image, you can mount a specific file as if it would be a file system. And these patches, or as it now is in the stock kernel, provides you with a cryptographic layer in between your actual file and the file system. So everything that goes into that file system will be encrypted. And as I said earlier, it's now included in the stock Linux kernel and available to anyone, as is dmcrypt. And of course, this gives everybody who runs Linux the opportunity to use these kind of solutions. I myself use Mac OS X, and it has a very similar solution to the loop crypto. And as I said, it's been deprecated, but anybody who actually used it before is probably going to use it for a long time as well. So, when you set up a crypto loop, you have to do keying, and it's done using the IOCTL function call. And there are two different programs that can do this for you by default. That is mount and LO setup. They are part of the util Linux package. And when this whole thing started out with the 2.2 series kernel from and the patches from kernel.i.org, the patches for util Linux wasn't approved by the author of util Linux, and therefore, for some reason, a number of people actually wrote their own patches, and there's a flourish of different versions of util Linux patches out there that, for a number of different reasons, are incompatible with each other. The version that is distributed today, and I assume that the author finally accepted the patches, is not very good. So it has a number of shortcomings, and for these reasons, several different Linux distributions have their own patched version of util Linux and the LO setup and mount utility that actually interprets what you're trying to do differently. So, for instance, Debian hashes the password into key before it uses it at the key, while the stock util Linux doesn't. So, if you're using Debian, for instance, and then switch to another distribution, you might not be able to access your crypto loop. From the kernel perspective, there's no difference between the encrypto, the keys being inputted. But since the key is inputted in different ways, using different version of LO setup or mount, the result might not be what you've actually expected. Also, I will go into this later, but there's actually a few bugs in util Linux that causes it to behave differently even if you have the same version. So might be worth noting that this is not a very good solution. But on the other hand, when we started out with this, it was the only solution available to us. So I know that there are a lot of people who use Cryptoloop, and actually DMCrypt is partially compatible with Cryptoloop as well and has the same shortcomings for the same reasons. So what you have to remember is that it uses the IOCTL, and you have two different options, mount or allow setup, that you can use to input your key. So I know that this is really, really tiny for those people, those of you back there, but I'm going to try to explain anyway. Cryptoloop is a very, very simple solution. So when you input your key and you set up your Cryptoloop or your loopback device, it creates one of these structures in the kernel. It just allocates memory for this structure and then it inputs it. So somewhere in the kernel you will find this key structure here. And there's two or three different things that I find very interesting. First you have this character array here with the file name. And then you have a character array with a crypto name. And then we have the key. And all of them are a fixed size. So for instance here, the file name and the crypto name has this LO name size. And I think it's like 128 characters or something. And then following straight after it, we have the encryption key and the crypto key size. This makes it very, very easy to search for this in memory. We have to know two things. Either we have to know the name of the encryptor, or we have to know the name of the file. So if we actually have gotten this far as to actually extract someone's memory and trying to search for the crypto key in memory, we probably know which crypto he is using, or we know the file name of the file we're trying to break into. So it's highly likely that we will be able to search for this. So in this example, I've created a memory dump using Xen. I just saved the memory of a running machine into a file, and then I did open it in a hex editor. And I know this is really fine print for you guys in the back, but here we can see the file name. So it's root secret stuff, and in hex. And then we have the algorithm of choice here, 2fish. So if I either know the encryption key, the file name, or the encryption algorithm used, I can use this to search for the length of the file, or the entire memory file. And here you can see the very, very secret key, my secret key. And as I said before, there are different versions of util Linux out there and allow setup, and this one doesn't hash the key. So here you can read the key in plain text. It will pad it up to the required size with null bytes, and at the end here we have the encryption key length 20, that's 32 bytes, 256 bit keys. And this is a really, really bad way to handle keys. But as I said before, the default version that is included in util Linux behaves this way. So, what if we have, for instance, Debian instead? Debian chooses to hash the key, or rather hash your password into a key of the specific length. Here we have another example, the name loop file. It's a bit shorter, so it might be harder to find, but if we know the name, we can search for it. The same with AES. It's a very short string, so if you search all of the memory for AES, you're going to end up with like a billion hits. But since we know that it will be null padded up to the fixed length, we can search for AES and then a lot of null pads. So it's actually quite easy to search for as well, because in a function name or in a variable name or something like that, it will not be null padded. So since we know how long it is, we also know where the key starts. So even if the key started with a null, we would still know where it starts because of the fixed length. So here we have a binary key, and it ends with the encryption key length. So it knows it ends with 20 always, or of course it could be 128 bits as well, but that's not very common. It could also be 192 bits, I believe. Anyhow, since we know where it starts, we know how long it is. So this one is hashed, which makes it a bit more troublesome if you have the wrong setup to use. But let's start with how to reuse the key for clear text. When you're using CryptoLoop, reusing a clear text key is very simple. You just input a clear text key. We doesn't have to bother with the length of the key or anything because it's always null padded. So we simply use the LO setup tool -e 2fish loop 0 and the data loop file that we want to go into. I believe my example is wrong here because it was named secret file or something. Anyhow, we just input a password, my secret key, and we can use, for instance, tune to FS or something to check that we actually got a file system there that is working correctly. So it's basically very, very, very simple to use. So then we come to the binary keys. The binary keys are a lot harder to use. Util Linux, as it comes by default, has a fence post off by 1 bug. For one reason or another, they choose to always put in a null byte on the last character. So even if you input a full 32 byte as your key, it will always truncate it and input a 0 at the end. So if we have a key that is hashed, for instance, by Debian, and we have it in a binary file, and we input it to LO setup as a string and say, please don't hash this, I want to use this as my key, it will truncate it, and the end byte will always be 0. So this might be interesting as well, because you think you're using a 256-bit key, but you're actually using a 248-bit key because the last 8 bits are always 0. And this makes it very, very difficult for us to input a key that is actually 256 bits. So it's virtually impossible. We have another problem as well. We're using string copy. A string copy doesn't like certain characters, for instance, null. So we're not going to be able to input a key that contains null in it. But in this example, I have patched my LO setup to allow for 32-byte keys, and I have a crypto key that doesn't actually contain nulls. So in this case, I'll be able to use like Perl or whatever hex editor you like to input your key into a file, and I can like just cat it and pipe it into LO setup because it has the P0 option to identify a file descriptor to read a key from. This isn't the only option available to us because, as I said earlier, dencrypt is compatible to certain lengths with CryptoLoop. So we could actually use dencrypt that uses hex keys as well. But it's difficult to input this kind of key using the stock LO setup. And even if you have a patched version, from instance Debian or Ubuntu, that actually does hash the key, you don't want to hash the key, you want to use the -n flag or something to tell it not to hash the key, and then it will revoke and go into this xstring copy function that is actually very, very broken, and you will end up with a truncated key anyway. To handle a key, a binary key as a string, causes other problems as well. We can't have certain characters in it, we can't have line feed, for instance, we can't have null in it, and there's a whole bunch of other characters that we can't use either because it's going to be interpreted by my shell or my keyboard or the kernel or the string copy function or whatever. So CryptoLoop being keyed by Util Linux is actually broken from the beginning. But we can input our hashed or binary key once we've extracted it, and then we can access the data. And as I said before, finding the actual key is as simple as loading your memory dump into a hex editor and just doing a plain text search for the crypto or the file name. So it's very, very, very simple. So let's have a look at dencrypt because it's a bit more trickier. It was introduced in the 2.5 or 2.6 series kernel. It uses the crypto API, as does recent versions of CryptoLoop as well. It's intended to be a replacement for CryptoLoop. As I said before, there's been different versions of CryptoLoop. The Loop OS author has a lot to say about the security of CryptoLoop. and dencrypt is partially compatible with Cryptoloop. And if you've read about the problems, or like there's a plain text fingerprinting attack on Cryptoloop, this is also valid for dencrypt since they are compatible at the block level. They actually have the same type of problems. But they have introduced some kind of IV segmenting thingy to try to solve that. But if you have a file with a known fingerprint in it on your Cryptoloop, the bad guys will be able to find it. They won't be able to decrypt it, but they know that it is there. So if you have this pirated movie or something. Anyhow, it uses the Crypto API, and it is supposed to replace Cryptoloop. So, keying. The keys are introduced to the kernel by an IOCTL, and dencrypt is part of the dev mapper infrastructure in the Linux kernel. So it uses the libdev mapper, which is like a common framework for talking to the device mapper. And there are 3 different solutions for keying. We can use DM setup, which is kind of awkward to use, but it gives us like a raw interface into libdev mapper, and the IOCTL is used. So we can set up different kinds of cryptographic solutions. We have crypt setup, which is very, very easy to use. It has a good mount page, and I believe most people would prefer to use crypt setup. And then we have crypt setup LUX. And LUX stands for Linux Unified Key Setup, or something similar to that. And LUX actually creates a small header at the start of your cryptographic partition in order to be able to save information about your crypto, like your key length and your IV and perhaps your cryptographic algorithm of choice and the size of the partition and stuff like that. So there's a small little header up there. This actually makes it very easy for the user, but it also makes it easy for the forensic officer trying to find your encrypted partition. So from a security perspective, I would never recommend anyone using the LUX setup unless you're like stupid and don't know how to use DM setup or crypt setup, because it's going to be really, really easy to find it. Then I don't even have to guess your encryption algorithm because it's going to be documented in the LUX setup. Dencrypt uses hexadecimal keys for keying, so we don't have any problem with the null bytes or stuff like that. So it's very easy to extract and reuse the keys in that sense. So this is going to be really hard to read, but this is the crypt config, which is the struct used by dencrypt to hold your encryption information, encryption key. And if we compare this to the structure we had for Cryptoloop, we can see that there are no character arrays here, so there's no easy thing to search for. All we have are a lot of pointers and some fixed values, and then at the bottom we have the crypto key, which is just an empty character array that will contain the key. So from this we can conclude that there's no easy way to find this, even if you know the file name, even if you know the encryption. But on the other hand, we know that right after this struct will be the key. So how do we find the key? Well, we know that we have kernel pointers, and we know that the kernel memory is always located in the same place. So I've created an if statement that verifies if all of these pointers has a value above 0xC00000 something, because we know that all the kernel memory will be resided there. And also we have some fixed value stuff. We have the key size. It will probably be 16 or 32. It could be 192 as well, but anyway. And then we have the IV offset, which should be 0 always. There's well, there are a few cases where you want to use another offset, but most people will use 0. I had a friend who actually tried this on his computer, and it turns out the IV gen private is not always a kernel pointer. Sometimes it's just a value. I don't know why, but I could update the software later on. The program to do this is included in my paper, and the paper is available on the website. So if you want to try this at home, please do. So if I have a memory dump and I run this program, it will simply output the key in hexadecimal form. So it will search the entire length of your memory dump byte by byte and compare it to this if statement, and if it's true, it will print the key. Very, very simple. No magic at all. So, how do we reuse the keys? So, we have a memory dump, we got the key, we have it in hexadecimal form, and we want to reuse it. First of all, dmcrypt doesn't actually work with files at all. It works with devices. That's one of the main differences. So, in order to access a file as a device, we have to set up a LO setup first. So, we loopback mount our secret file on dev loop 0. Then we use the blockdev command to get the size of the device, and then we can use dm setup, which has this hugely complex syntax. But anyhow, start, size, we want to use the crypt dm target algorithm, the abbreviated key, something something, loop something, pipe, dm setup. And since we don't have the problem with the null bytes or the cutoff key lengths and stuff like that, this should work like right out of the box. No problems at all. So, what about LUX? Well, as I said before, LUX stores a small header right before your encrypted data, and this header contains information about your encryption scheme, let's say that. But from the kernel point of view, it doesn't see that. It's just a keying program used to input the right key. So it uses the offset feature of the DM layer in order to jump past the header with the cryptographic information in it, and that is and just the rest of it is your encrypted partition. The offset is stored in the struct. See, we can find it in the key storage. Yeah, there it is. No, that's IV offset. Well, it's there somewhere. Anyhow, the software I wrote to do this actually outputs the offset, and the offset is calculated in 512 bytes blocks. So we have to offset when we try to access this partition. We do this with LO setup. That's the easiest way. We could do it straight with DM setup, but that's a bit complicated because we have to recalculate the size and stuff. So we simply use LO setup with a -O option, which is offset, multiply the number we got from key search by 512, and input it to LO setup. Then we use the blockdev software again to get the size of the device, and then we repeat the same thing. Echo, start, the size that we want to use, the crypt DM target, the algorithm, abbreviated key, something I don't know what it is, the device, something else. Then DM setup, create volume 1. That's it. It's not harder than that. So, what can we conclude from this little expedition into the crypto key world? Well, it's surprisingly easy. It's very, very easy to find and reuse your keys. All disk encryption systems are equally exposed. It's the same thing. You have to store your key somewhere, and when you're doing it in software, you have to store it in memory. Kernel memory will never be swapped out, but if you're using one of the userland encryption functions like CFS, you always run the risk of actually by accident writing your cryptographic key to your disk. But from a kernel perspective, it shouldn't end up on a swap at least. Don't lose your memory. That's very, very important. If someone actually is able to get hold of your kernel memory or a memory dump of your entire memory, they will be able to access your encrypted file systems. It's not difficult, it's very easy, and you'll have to make sure that no one does that. So, half an hour, perfect. Memory imaging techniques. when I wrote my paper, I had the assumption that you have to start out with a memory dump and you have to get that somehow. And during all of this, I started thinking about what kind of ways one would be able to acquire someone else's memory. How can you dump someone's disk, someone's memory without them knowing? How can you lose your memory without knowing it? So I did some research on this as well, and this is a well-researched area. Let me tell you that. There are a lot of people doing research in this area, and it's scary stuff. First of all, we have software imaging. Most modern operating systems like Unix and Windows and Mac OS X and everything else has like pseudo devices that allows you to access all of the physical memory. This of course requires root privileges, but still you can access all of the memory. Then we have like Hibernation files. If you have a normal computer, it has a fixed size battery, and when it runs out of battery, it has to do something. And one of the options is writing the entire content of RAM to disk into a Hibernation file that allows it to come back up again. If your cryptographic keys is in that memory, they will end up on your disk. And if I steal your laptop and I know that you have Hibernation on, all I have to do is wait, because I know it's going to write its memory contents to disk. So that's just a waiting game. I was at the CCC Congress this year, or last year, and there was this guy who talked about Mac OS X. And Mac OS X did something really smart. When it wanted to hibernate, it encrypted the Hibernation file. But in order to restore the Hibernation file, it also wrote the crypto keys to disk as well. So kind of stupid. Some specific types of platforms has different kind of firmware breakpoints, particularly the Spark platform. So you can actually press this magic key combination on your console, and everything holds and goes into this firmware where you can play around with it, and you can dump your memory. Linux has the magic sysrequest keyboard combination, and from what I've heard, you can actually dump the memory from there, but I haven't verified this myself. But you always run the risk of someone doing this on your computer. And then of course we have the whole scene of virtualization software. When I did my research on this, I used Xen and just saved the content of my Xen virtual machine into a file and read the file, the crypto keys from there. But there's a whole lot of other type of virtualization software out there that people use. Xen actually has this wonderful live migration thing where you can send all of your memory across the network to another machine. Sounds wonderful, doesn't it? And if you set up that wrong, or if you set up it unauthenticated, someone can dump your memory from remote. Not very good. So software imaging technique is a threat, even though it is a bit more complicated, or it takes physical access to the machine in most cases. But let's face it, don't use crypto in your virtual machines. And then we have the whole area of hardware. There are some guys who built a custom-made PCI card that you can put in your machine to dump memory. They could hold the CPU and then do DMA access to all of the memory and dump it. One glitch though, you can't like insert a PCI card afterwards. You had to boot the machine with this PCI card in it. But on the other hand, modern platforms has hot swappable PCI slots. So you can like insert a PCI card in runtime. So if they get physical access to your hardware, they'll be able to input a PCI card in runtime. Then we of course have the option of custom-built pcmci cards. The pcmci bus, or one of the latest versions of it, has DMI access. So I could build a custom-made card, insert it into your computer, and have access to all of your memory. So is there any such card on the market today? Yeah, there is. I can buy myself a pcmci firewire card. I have one of these here. What do you think happens if I insert this into your machine, your laptop? Well, a modern computer will happily find this card and load the drivers for it. So I can dump your memory by inserting this card into your computer, given that you have drivers for this card. If we look at Windows, for instance, it will happily load the drivers. And on the other hand, I would have to pretend that I am an iPod in order to get DMA access to all of your memory, but it will work. Modern Linux distributions such as Red Hat, Ubuntu, Debian also have drivers for this card. So all of you who uses one of those operating systems and has the driver by default are vulnerable for this. I'm not really sure why the card needs the drivers, because it's a hardware thing to read the memory. It might be that if I buy a different card, I don't need the drivers, but I don't know. And of course, I could build myself a custom-built pcmci card and read the memory that way. I don't need to actually pay the 12 euros for this card. I could spend $1 billion designing my own card if I had the money or time. And machines like mine, for instance, has firewire built in to begin with. And my Macintosh here, it will happily initialize the firewire card in the firmware when it boots. So I don't even need the drivers in my operating system for this to function. By the way, the scariest part is definitely the pcmci card. So disable your pcmci port. Epoxy is a good option. Then we come to another different area. Residual memory. The same guy who did the research, I'm going to find his name, Wietse Venema at IBM, did an interesting test with IBM laptops. They created something they called stamps. A stamp was just a sequential number and a cryptographic checksum. And then they filled their memory with that. And then they rebooted their computer. Or rather, they did a lot of different scenarios, and then they checked how many those stamps were still in memory. So what if I run it as a web server for 14 days? What happens? How many stamps are left? And what if I reboot my computer? How many stamps are left? What if I turn my laptop off? How long does those stamps remain in memory? And this guy actually had a Thinkpad T30 turned off for 30 seconds, and when he booted it again, the stamps were still there. So I figured, let's try this on this laptop. So I wrote a small program that filled up all of the memory with a single string. I will Google before asking stupid questions. So it allocates 1 megabyte of memory, writes this string into all of it, allocates 1 megabyte more, and does it over and over again until it gets killed by the out-of-memory thingy. And then I just reboot it. Ctrl-alt-delete, reboot, shut down, whatever. And reboots again into Linux with init equals bin bash to shrink the memory usage, and I grep from /proc kcore and grep for Google. How many here things that I got to hit? Yeah, you're right. The memory just riddled with it. It's everywhere. And it turns out that in the original IBM computers, when the computer starts up, it does a memory test. And this memory test includes writing different patterns to all of the memory, and then reading them back again, and then writing another pattern just to test that all of the memory is actually functional. But this takes a lot of time, and people don't want to wait for the computers to boot. So a lot of computers have this turned off completely, or they have it set to just do it when they do a cold start, or they have it set to only do on the 641st case of the memory or something like that. So it doesn't actually do this all the time. So there's actually quite a good chance that if I get access to your computer, press Ctrl-alt-delete on it, boots from a CD or a USB stick, that your crypto key will remain in memory long enough for me to actually read it. As long as I don't overwrite it, as long as I don't turn the computer off, it will remain there intact. DM setup, or DM crypt, has this really wonderful feature of removing the key or overwriting the key from memory when you deallocate the DM setup thingy. But when you press Ctrl-alt-delete on a normal Linux computer, it won't do that, because in the shutdown scripts, there is no shutdown script to remove your DM crypt. So even if I do a clean shutdown of your computer, it won't remove it. So you could remember that, unmounting your crypto setup before rebooting. And you could enable the fully memory test if you want to. So, memory imaging conclusions. Physical access is very dangerous. If someone gets physical access to your computer, it's highly likely that they will be able to extract the crypto key as long as it's still turned on. There are a number of different venues that they could try, and they could try them in order. They could try with a pcmci card first, then they could try to reboot the computer. Perhaps they could even like reset the computer. They can insert a PCI card if you have like hot plug PCI ports. I think that on a modern laptop you can even hot plug the mini PCI cards. So there's a lot of different venues here for actually making a forensically sound image of your computer hardware or computer memory. So you want to disable firewire if you can. Epoxy is a good solution. You want to disable your pcmci port. Epoxy, again, is a good solution. And you want to disable hibernation. You never ever want your computer to hibernate, because even if you remove your cryptographic key from memory, there's a lot of other interesting stuff in computer memory that we could access. The keyboard buffer, for instance. When you entered your password or passphrase, there's a keyboard buffer in there, and that keyboard buffer is somewhere in memory. There's also all of your other passwords. There's the page cache. When you access a file on your encrypted file system, Linux will by default copy that into a buffer called the page cache. So your files that you access on your encrypted file system will be copied in clear text into memory, and that memory will remain intact until it's needed again. And so even if you unmount your crypto partition and then just shut down, it won't need that memory again, and it will remain in memory. And especially if you go into hibernation, all of these files will remain. And this guy at IBM actually did file recovery from the Microsoft EFS encryption scheme using files from the page cache or data from the page cache to recover files. You want to disable ctrl-alt-delete or any other way to like reboot your computer. And you never ever want to do encryption in virtual machines. That's just plain stupid. I know that, for instance, Xen and virtual PC or virtual server, or whatever it's called for the Microsoft platform, has this wonderful option to like save the state of your machine when it's rebooting. So if you reboot it, it will write all of your memory to disk so that it can like continue when you boot it back up again. And this sounds really nice, unless you have cryptographic keys in that memory that will be written to disk in clear text. You might want to have a BIOS power on password, so that if someone actually is able to get physical access and reboot your password, reboot your machine, it will ask for the password. We tried this on this machine here, and for one reason or another, it only asks for password at cold boot. So it's not really that useful, but it feels better anyway. And you want the auto-locking screensaver. You really want your computer to go into to lock the console when you leave it. And there's a whole debate going on how long you should wait before you enable the screensaver, but the main thing is that you want to enable the screensaver. So, I think that was it.
You didn't cover a previous program that you refer, like TrueCrypt or BestCrypt or things like that, but this is only for lack of time?
Actually, I decided to begin with I wanted to look at TrueCrypt and DMCrypt. But since CryptoLoop and DMCrypt is default in the Linux kernel, I decided to look at them. But BestCrypt and TrueCrypt has the same problem. It needs to store the cryptographic keys in memory, and wherever the memory goes, so does the key.
Could you maybe go into a bit more detail on how this pcmcia firewire thing works? Or where would you actually put the memory? Or is this?
Okay, so the firewire actually has this really nice feature that it allows you to do DMA access over firewire. So if I plug these two computers together by firewire, this computer can read the entire memory of this computer using DMA. So direct memory access from hardware. But if this computer doesn't actually have a firewire port, I need to introduce the firewire port, and an easy way to do that is by the pcmci card. So I plug the pcmci card in, it loads the drivers, and suddenly I can interface these two computers and read the entire memory to this machine. So I have to have the correct software on my computer to be able to do this. But this software is available since many years because people have been researching doing firewire memory dumps for quite a number of years now. The only problem is that some machines doesn't have firewire, and this card solved that problem.
I think I'm the guy, either me or Ralph was the fellow talking about the Hibernate image on macOS 10 at the Congress last year. So I did some more reversing on that, and it turns out that it doesn't actually encrypt the sleep image. I've never found one in the wild. I've inspected over 200 Macs legitimately and have found that none of them have an encrypted Hibernate image, and by default, anytime you put an x86 macOS 10 machine to sleep, if it's a laptop, it'll write out var VM sleep image, and it's unencrypted. On the offhand chance that you did happen to find one that was encrypted, though, it's either stored in some, like in the EFI or the open firmware memory or the disk CMOS backup stuff. And so all you have to do is ensure that when you boot the machine, you don't hit the mock kernel entry point, and it won't free those variables. So if you boot off, say, Refit, the EFI shell utility, you can dump NVRAM without having to worry about it, and you can actually extract the sleep image and do all that stuff as well. But inside the Hibernate image, you have encrypted swap keys. So have you done any research about recovering encrypted swap files? Because
no, actually I haven't. This is basically what I've done. I wanted to see if it was possible to like recover the keys and how difficult it would be to reuse them. So it's the reusing step that I've been researching. And it turns out that reusing the keys is actually quite simple once you know how to do it. And as I said before, if I had more time, I could research other cryptographic system as well. For instance, File Vault for Mac OS X. But
don't bother researching File Vault. It's not interesting.
I mean, all of them have the same problem. They store the crypto keys in memory, and wherever the memory goes into Hibernation files, you lose it via DMA or anything, your crypto keys are gone as well.
Maybe a follow-up question on this one. When you store your Hibernation file in an encrypted swap image, is it secure?
I believe the question was, what if you store your Hibernation file in an encrypted swap image?
Yeah.
Yes. The problem is, when you return from sleep, or when you boot again, you need the key to be able to boot up again. And for instance, Mac OS X or Windows, they simply have no simple way to input the correct key. I know that Suspend 2 for Linux actually has the capability of doing this. You can boot into an init.rd and input your key, and it will be able to decrypt the Hibernation image and launch into that Hibernation image. So yes, that is absolutely possible.
Okay.
Yes, once you're running again and you have your key in memory, I can recover it using, for instance, the firewire card.
A friend of mine told me that there is a possibility.
I'm terribly sorry, I can't hear you.
Okay, they're having fun. A friend of mine told me that the Linux kernel has the possibility to disable the firewire feature that makes the DMA transfer possible. Is that right?
Yes. The question was, can you disable the firewire feature? And yes, a normal computer or a normal Linux installation with or without firewire will allow you to do DMA. But there is an option for your DMA, for the firewire to disable DMA. And if you use gearsec, for instance, it will have this disabled by default. So yes, it is perfectly possible to disable it by the driver. so that when I insert this card, nothing will happen. On the other hand, if you're actually using firewire, it will be painfully slow without DMA.
To my knowledge, the Linux kernel changed the default, and all recent kernel have a so-called raw driver for the firewire. And unless you load that, the kernel is fine. Only if you load the raw driver or enable that raw mode, the DMA hacks work. And I think the older kernels have the default wrong, but all recent kernels should be fine, to my knowledge.
I haven't researched that actually.
Yeah.
What I did was I tried it and it worked. So the interesting part is that you will actually have to take measures yourself, or the kernel developers have to take measures in order to secure this. By default, most operating systems and by default most users are vulnerable to this problem.
And about the hibernation to a encrypted partition, it also works fine with the stock software suspend. You can simply boot from an unencrypted boot partition, a normal kernel with an init rumfs, and that can then set up an encrypted root and an encrypted swap partition, which you can also use to resume from an hibernated kernel, so that works fine.
Yes, Linux has the software suspend feature. That means that Linux is doing the hibernation stuff. But on the other hand, a lot of laptops has the hibernation feature built into the BIOS. And so if you enable this, it will actually do suspend of your Linux laptop whether or not you like it, because the BIOS thinks, oh, I'm running out of battery, let's save everything. So if you have this feature enabled in your BIOS, it will do hibernation whether or not you like it.
If you want to use hibernation together with encryption, would it be the best thing to put it on an LVM volume?
I didn't hear the question.
Wouldn't it be the best thing to have an LVM volume and then store the whole system in that LVM volume together with a swap partition?
If it would be the best thing to have the whole file system and the swap partition in the crypto file system?
Yes.
Yes, of course. What you want to do is you want to encrypt everything that you can get your hands over and encrypt. Because when they come and get you, they can use all of the little pieces that they find to try to sort out together what your password for the encryption is, for instance. So let's say you have a root file system that is unencrypted, and then you have your secret data volume. They're going to brute force your passwords from your password file and try to use them in the hopes that you have used similar passwords. Or for instance, just an easy thing. Let's say I brute force your password from your password file, and then I discover that the word you selected for your root password is a word in German, or perhaps a word in Spanish. Then I can use a Spanish word list to attack your encrypted file system, because I can make an educated guess that it would be something similar. So encrypt everything.
Okay. You mentioned that you can find remainings of files in the file system cache after you unmounted the cryptical volume with crypto setup. Have you actually verified this? Because I guess that the Linux cache is a block file system cache, a block device cache, and should cache the encrypted pages of the block device and not the unencrypted pages of my files?
It depends on the cryptographic system that you're using. The guy who actually researched this did it on Windows, and he wanted to recover files from the EFS file system. But if you look at the block layer of Linux, it is highly likely that it has one encrypted page cache and one unencrypted page cache, but I'm not really sure of this. On the other hand, there will definitely be a queue where there comes an unencrypted block into the queue, and then it is supposed to write this. And since dencrypt and encrypt are running in a pseudo user space, kind of like a kernel thread, there will definitely be a queue for these that is in memory. So even if the block layer doesn't actually, page cache doesn't actually store it, there will definitely be a time when it is written to unencrypted kernel memory. And if we are unlucky, that page isn't used again, and then it will remain there for inevitable time.
There actually is another method of obtaining memory dumps. Some remote management cards like Hewlett-Packard's ILO, the integrated lights out management cards, are said to be able to dump memory. Have you done research on that?
The question was, have I done any research on other types of remote memory imaging techniques, for instance, the compact ILO or the Del DRAC or whatever it's called? No, I haven't. My research went mainly into how do I reuse the keys once I find them, and then I went to like researching a bit what kind of ways do we have to make a copy of the memory. And of course, any type of hardware that interacts in that way, such as the ILO, or rather, as soon as you have a PCI card that you can somehow manage, it's highly likely that you will be able to recover memory, because PCI cards has DMA access. And as soon as you have DMA access, you can access all of the memory and you can read it out, everything. On the other hand, there are machines coming out now that has something they call IO-MMU, IO Memory Management Unit, that is able to set up the memory management unit in a way that it can control which PCI card is able to access which page. And you could also think that it might be possible to store your cryptographic key somewhere where it's unlikely that they will be able to read it. For instance, in your graphic cards, perhaps. So if they do a memory dump, they won't get the memory from the graphics card as well. So I don't know. There are theories about that. I'm not an expert on it.
Just another thing.
Yes?
There was some research done by David Picton on SSH agent keys. He was able to read SSH keys from memory dumps, even if the SSH agent had a timeout set, which was which has run through. You can find the paper online under the name of David Picton.
Oh, okay. I'll look into that. It was about that you can read keys from the SSH agent. And the interesting thing about this is that the SSH agent runs in user space. So that one always runs the risk of having its memory written to swap. Some operating systems allow you to like mark a certain page and say, okay, never write this page to swap. It contains sensitive material. On the other hand, there are operating systems that doesn't support it. And there are operating systems that actually says, okay, and then do it anyway. And then we come into the whole hibernation thing again. So everywhere where you have keys in memory, be it SSH keys, be it dmcrypt, cryptoloop, bestcrypt, EFS, whatever, as long as you have your keys in memory and you lose that memory, you're going to lose these cryptographic keys as well.
Another question. You mentioned watermarking attacks on encrypted partitions earlier. I thought this issue was resolved by using the XTS or ESSIV mode of operation, or did you mean something different?
The question was regarding the fingerprinting in Cryptoloop. Well, you can actually like write plain text data to a Cryptoloop and then somehow prove that the data is there. I haven't done any research on that at all. I've just read that it's a fact, and yes, I think they've solved that somehow. But the problem is in Cryptoloop. But since dmcrypt is actually compatible, the problem remains in dmcrypt as well. But there are options for dmcrypt that will solve this problem because it uses some like initialization vector that is different somehow. So yes, the problem is solved in dmcrypt, but you have to enable it because otherwise it will run in compatibility mode and have the same problem.
And another question, while it's good to be aware of this issue, I don't see how you can actually do anything against having the key in memory unless you use trusted hardware. Or
I didn't.
If you do encrypt, if you do software encryption of your partition, you do need the key somewhere in hardware. So it's quite unavoidable that you can get to the key if you get to the memory. So you have to either protect the memory, or you have to use trusted hardware. So I don't really think it's really a vulnerability, more like expected behavior.
So did I interpret the question as this is not really a vulnerability, it's like an expected problem?
Yes.
Yes, and yeah, you're right, absolutely. This is not a vulnerability. I mean, this is the way it works. This is the way it is. The important thing is that you know about it. It works this way. And the important thing is that you know that when I enable Hibernation, it's going to write my keys to disk. So I just basically shoot my foot off when I enable Hibernation. And the same thing with firewire. Firewire can do this. It's not an exploit, it's not a vulnerability, it's just the way it is designed. So if you think it's a feature that someone else can read your memory by this cable, well, then it's a feature. If it's a problem for you, disable firewire.
Further questions?
All right.
Okay, thank you very much.